Hello everybody, my name is Shweta and today I'm going to talk about learning to walk as my final project for the deep reinforcement learning project. So I chose this competition from the Crowd AI website where we have to try to make this simulated muscles learn to walk. The context or the introduction to this project is that when a person who's suffering from many neurological disorders or cerebral palsy, and when he goes under these surgeries, so after the surgeries, what is the outcome that we predict for that person to walk? So this would kind of help in that area. This is my understanding of the introduction. What this does is it basically the objective here is to make a motor control that would actually take in like your observations of the uh, the the observations of the pelvis, head, or foot, or other positions, angles, velocities, and give an output of a musculoskeletal model with 18 muscles to control. So these 18 muscles would show which one are active or which ones are inactive while moving. The main goal is to make this bot walk in a position in a possible way in like every 5 seconds, and you should restrict falling, or you should restrict the pelvis angle that is present in the program. So the toolkit that I've used for running this program is a Linux machine, KeresRL, Python that works on Anaconda 2, and OpenSimRL. In the OpenSimRL, I've used the Gate environment, which uses the Gate model to run this program. Let's see. The first thing that I want to talk about is the algorithm actually that we've used for this for uh, for for this problem to solve this motor control problem is the DDPG algorithm. So the DDPG algorithm is nothing but the deep deterministic policy gradients, which is actually which works on an actor-critic learning algorithm. So what it does is it's a model-free or an actor-critic algorithm, which is an off-policy algorithm that we see. My understanding of this algorithm is that it has a policy function which is known as the actor, and it has a value function which is known as the critic. So what happens is when your actor performs some action in the current state, the critic actually looks at those actions, and as simple as that, that it takes a temporal difference and gives the error signal for that state and the resultant reward. So accordingly, like this critic, it gives those values, the q values back, and if there is a termination of the episode, then it would sum up all the q values. But if I mean, it would also look at the q value function for the pelvis angle or for the 5 seconds, whether it's falling in the 5 seconds or no. So the output of the critic drives learning from both actor and critic in the deep learning reinforcement program. What happens is, I mean, we also have DQN, but DQN works for a discrete area, whereas here we want to see continuous motions from the OpenSim gym. So what happens is, like, if you're moving in, like, your movements are continuous. So in a continuous environment, we would need something that would continuously take those explorations and then exploit on them. But what happens in DQN is, so basically in DQN, it takes discretized data. It doesn't take the continuous environments. So if you take DQN, what the algorithm would basically do is it would take the highest rewards and it would choose them as the best actions and only perform in that manner. But what deep deterministic policy gradient does is it would allow you to perform exploration and exploitation in a continuous form, and then it would know that, okay, which are the actions which would not allow you to fall in our case. So here is the model one that I had implemented. Certainly, I've implemented like 2 to 3 models by changing their hyperparameters and changing their layers. The initial base code was taken from the KeresRL GitHub link that is shared on if you Google search, you would get the KeresRL link. So this is the actor where initially we are taking 31 inputs. The 31 inputs come from a PY file, the human PY file that is present. So What this py file does is it actually configures those so it'll configure the joints and it'll configure the movements. So this is the human py file that I've been talking about, and these are the 31 configurations that it chooses. So here you can see there are 31 possible ways where it has the positions, the accelerations, the velocities, the position of the left foot, right foot, the head, the pelvis, and you could also see like how it is set up here. Another hyperparameter tuning that I was doing was initially this variable started from 0 and then I started changing the parameters from 0 to 0.2 to see if there is any difference in the network of how it takes these observations and tries to train on it. This is one thing that I had changed here. Another thing that you can see is there is a function of, so this is the configuration function. The other function that you can see is there is a function of the pelvis. So if the pelvis is less than 0.7, then the episode would terminate. But so basically here they had restricted it to 0.7, but I wanted to try what would happen if it was 0.5 or if it was 0.8, what would happen to the network as it trains over. These were some changes that I had made in this file. The other thing that I wanted to talk about, so this is the network where you take in the 31 inputs as I just showed you, and those 31 inputs are then given in the form of 18 muscular actions. And I have used the sigmoid function here to basically see which action would be given the most importance here. So one of them would be given like an importance here of um, which one to be active and which one to be inactive. And this is the critic function here. So the critic function takes the state and the action both. This is a layer where it merges out the action input and the state inputs. And once it merges out those state inputs, it gets like it gets 49 inputs. That is 31 observation state and 18 muscular state actions that we've just spoken about. I tried using like different layers here with 128 neurons and then into 32 and the 32. So basically what this does is it then builds a critic model, which is shown here. The critic model, as I said, takes the observation input and the action input and gives one value as the output. So since it was one value, I thought of taking the linear activation function here. So this is the DDPG agent that has been taken from the the Keras RL repository, which talks about how this DDPG agent works. There is a random process which is generated. Initially, some randomness is given, where I tried changing here. It's still given like 0.15 and mu is 0, but I tried changing the sigma and the theta so that I would know that how the randomness would affect the how it would have an effect on the model. And then this is fitted into the DDPG agent. So what the agent does is it actually takes the critic, the actor and the randomness and the number of warm-up steps, and then this would compile on I've chosen the Adam optimizer here. So Adam optimizer with a learning rate of 0.001 and with a matrix of mean absolute error. But I had tried changing the learning rates from 0.001 to 0.1 or 0.002, and I wanted to see how it works on the network. Also, I had tried changing this to RMS propagation versus Adam. So what I thought of while taking the RMS propagation is how they treat their optimization according to the learning rates. So that is the main difference that I thought that RMS propagation and Adam would take, is how they would train on the learning rates. And so I performed these experimental logs. Another experiment that you can see here is I had increased the number of steps. So by increasing the number of steps, as you can see, that man is trying to walk and he's getting out of the blue scale square that has been drawn, and he is trying to be taken like some baby steps here. So these are the three models that I was talking about. One, so I would show you like how the models look like, but the best award I got for the model 2 with increased number of steps. Uh, let me just show you like how the models look like. So the models, all this is present on the Git repository. The scripts are here. The model 2 basically looks like this, where I've chosen this as the network here. This is the actor. This is the critic, and this is basically the DDPG agent that I was just showing you. This is about model 2, sorry, and this is about model 1. Model 1 was taken like with 332 dense layers and with sigmoid and linear function and with the same criteria here. Let's see about model 3. Model 3 here I try to change the randomness and the randomness with the number of layers. So here you can see like I've changed the 64 dense layer here, and with the critic also having 64 dense layers here. And if you can see that I've used the Gaussian white noise here, I try to change basically, so I didn't take a theta here, I took a sigma here. And if you see that the learning rate is 0.002 here in the DDPG model 3, what I've taken is uh, again here, like what I've taken is I've taken the Gaussian white noise. So this is, and I've reduced a layer here. So this is about the different outputs that the different layers that I was trying to take, and this is the output that I received. And this is the model 2 that I was just talking about. Let's see some of the observation logs that I was trying to change. So this is some of the observation logs. Like I tried to change the randomness, the optimizers, the number of steps. There was a time when I ran this program for around 70,000 steps, and it was giving me some positive rewards. The pelvis angle that I was talking about, the initialization, the activation functions from ReLU to TAN-H. So TAN-H actually works in a space which is and real line bounded closely to each other. In that case, TAN-H would be a good activation function. But according to me, when I observed it on a large number of the increased number of steps, the episode kind of ended early for me. So at that point, I thought maybe TANH wouldn't be a good function. But yes, for my future work, I would see like how TANH as an activation function would help the bot move forward. These are some of the observations that I had received while performing some experimental logs, like initial training. And then when I change the number of layers, you can see how the bot is trying to pick his leg up and trying to walk. So these are some of the observations. This is when I had taken like number of steps to be increased. When the number of steps are increased, you can see how it is exploring and trying to move the knee points and the key joints. When it was at step number 22500, it tried to walk out, and as you can see, it has already stepped out of this area. When it was at 34,000, you can see how it is picking its leg up. Basically, you can see when it trains itself for more number of steps, you can see that you start getting positive rewards back, and the loss function is also getting lower and lower. This was model 1 that I implemented, and this was how the testing looked like. This was model 2 that I had implemented, and these were the rewards that were reached. So what I was doing was every time I performed model, the weights were saved, and on those saved weights, I ran the test. If you want to see the weights that are saved, the weights are saved here in the saved models folder on the Git. So these are some of the weights that are saved here, where it says that, okay, uh, the name of the model may be sample like initially, but then later when I was trying to do some changes, like make the initial value as 0.5 or make the pelvis angle as 0.8 or make the pelvis angle as 0.5 and see if it has run for 10,000 steps or no. So these are some of the weights that I changed, and these are some 10 to 12 models that I had tried on. So let's move on. As you can see here, so the rewards achieved are positive, and this is the third model where, this is the second model where I was getting a reward of 8.127. And accordingly, like I again tried changing the model 3, where I tried changing the random process, the randomness to Gaussian white noise. Here I was getting an output of 5.063. This is the comparison that I've just showed in the PPT. My future work would actually be to see how CDQN works, because CDQN is another like continuous DQN, which would help in looking into the model-free reinforcement learning. The model-free reinforcement learning would help better to achieve more rewards, and maybe would help in making the bot run. So that would be my future work. These are some of the literaries that I have read, and out of which the first one gives a basic idea of the DDPG algorithm. The second one is the main Git repository for Keras RL. The third one is how to understand the OpenSim RL function, OpenSim RL environment. The fourth one is a David Silver paper where it talks about DDPG algorithm, and the fourth one talks about the CDQN algorithm. So the Git repository has the demos and the GIFs. This is a demo that I had chosen. Like initially, when I didn't apply any algorithm, it was just falling and not training on anything. But later, when I applied a DDPG algorithm, this is one of the frame screenshots that I have taken to see how it trains on. So this is with the DDPG algorithm. This is how it is trying to learn to walk. Another folder which is important here is the demos and GIFs. So these are some of the screenshots that I had taken while performing different algorithms. So suppose if I had performed something on 10,000 steps, so this is how this is where it is basically showing that yes, I have performed the training on 10,000 steps, and when it was on 22,500, this is showing that it's actually trying to walk and it's moving out of the normal gradient. Something that you could also see is how you get the positive layers, or when the sample layers were changed, what was the training done on them, what were the other screenshots that were taken while training. So these are some of them where you get an increased reward with the number of steps taken. So this is 8.127, and the number of steps were also increased here. These are some of the screenshots that have been taken. These are the GIFs basically, which I just showed you on the Learn-To-Walk website, on the Git repository, which is present here. Yeah, so in the next video, we'll talk about how to pull this how to pull the models and the how to pull the models in the Docker image that I have just created. Thank you very much.